Hello, in the previous clips we have seen how to perform 2 degree of freedom control design in order to achieve robustness for the closed loop systems response to variation in plant model. We have seen that it can be employed to achieve a high degree of insensitivity to variation in the plant's gain, to variation in the plant's pole, and indeed to variation in multiple parameters of the plant including its gain and perhaps all its poles if that happens to be the case. So in this clip what we would look at are some of the notes in connection with 2 degree of freedom control and some of the issues associated with 2 degree of freedom control, and we shall see how these can be addressed. So the first point that I want to address is this apparently magical manner in which the transient response of a 2 degree of freedom control system becomes insensitive to variation in plant parameters. So what is it that is really going on behind the scenes that helps us to achieve such a high degree of insensitivity to variation in the plant's parameters? To understand this question, what I have done here is I have plotted the Bode plots of the plant alone, which has been shown as the red trace in this graph here, while the blue trace shows the Bode plot of the feedback controller times the plant. Now if you look at the gain crossover frequency of the plant alone, you see that it is quite small, it is close to about 0.2 radians per second. Whereas if you look at the gain crossover frequency of the plant times the controller, it is exceedingly large, it is about 42.8 radians per second. Now 42.8 radians per second as a number is significantly higher than the location where we wanted our dominant closed loop dynamics to lie, which was at minus 1.5 plus minus 2j. Hence what we see from the Bode plots of the feedback part of the 2 degree of freedom control system alone is that it is not really the feedback part of the control system that gives us the desired transient response. The desired transient response as dominated by the poles placed at minus 1.5 plus minus 2j is actually obtained from the pre-filter of the overall control system. So our 2 degree of freedom control system can be thought of as a cascade of two subsystems. One is the pre-filter and the second is the feedback control system. And we see from the Bode plot of the feedback control system that it is not the feedback system that gives us the desired transient response, because the feedback system has a bandwidth that is much higher than what has been dictated to us as a desired dominant closed loop pole positions. So the desired dominant closed loop pole positions are guaranteed to us primarily by the pre-filter. Then what is the role of the feedback control system? The role of the feedback control system is to deal with the uncertainty associated with the plant. It ensures that the high loop gain that the feedback control system achieves in open loop ensures very small variation in the response of the feedback part of the control system to changes in the plant parameters within the bandwidth that is of important to us, namely up to a corner frequency as dictated by the dominant dynamics of our feedback control or of our overall control system, namely minus 1.5 plus minus 2j. Hence we see that the role of making sure that the transient response is dictated by the poles at minus 1.5 plus minus 2j is taken up by the pre-filter, while the role of ensuring minimal variation in the overall transmission function due to variation in the plant parameters within the frequency range dictated by the dominant dynamics of the overall system is taken care of by the feedback control part of the overall system. So the 2 degree of freedom controller has a finely divided distribution of roles and responsibilities between the pre-filter and the feedback controller. The feedback controller is intended to deal with uncertainties associated with the plant, while the pre-filter is designed to give you the desired dominant dynamics for the overall transmission function relating the output to the reference. This is the first point that I wish to make. The second point has to do with the controller structure that we obtained in the course of the designs that we undertook over the last 3 clips. So if we look at the controller structure. In all cases the controller had a structure of the kind that has been shown here. It was of the form k times s plus z times s plus z bar divided by s plus p4 the square. Because we assume that the controller has coincident poles, we have the term s plus p4 the square appearing in the denominator, and we went over the elaborate design steps necessary to determine the locations of the z of the zeros z and z bar, which are intended to restrict the variation in the closed loop pole due to changes in the plant parameters. And the gain k of the feedback controller ensures that for the nominal value of the plant parameters, the closed loop poles are located exactly where we want them to be located, namely at PCL naught and PCL naught bar. Now if one were to draw the Bode plot of a controller that has this particular structure, we note that when we substitute s is equal to j omega and look at the magnitude of the controller's transfer function for frequencies that are below the corner frequencies of both the 0 as well as the poles of the controller, then the magnitude response will be flat as seen from the plot here. Now when we approach the corner frequency of the 0 z or z bar, then beyond this corner frequency there will be a 40 decibels per decade rise in the magnitude characteristics, because we have two zeros contributing to the rise in the magnitude characteristics. So this is a region where we have plus 40 decibels per decade rise in the magnitude characteristics. But then at some far away location we have the pole, two poles P4 and P5 which are coincident, and at that particular location we would have a minus 40 decibels per decade characteristic that gets added on to the plus 40 decibels per decade characteristic of the two zeros, and hence beyond that frequency we would once again have a flat characteristic, since these two contributions cancel each other out. So this is once again going to be about 0 dB per decade slope. What is a little worrisome about this characteristic is that for frequencies beyond P4 we note that the magnitude of the controller transfer function has to be quite high, namely around 80 decibels per decade. This may be okay because the example we considered was a peculiar one where we assumed very large variation in plant parameters and we imposed a restriction that the closed loop pole should vary by a very small amount in response to variation in the plant's parameters, and this is what has resulted in such a high magnitude for the controller's gain for frequencies beyond P4. What is more worrisome though is that this gain has to be maintained for all frequencies starting from P4 and all the way up. So all the way up to infinite frequency we need to have the magnitude characteristic of the controller be equal to 85 or so decibels, and this is an impractical proposition. There is no physical controller that can give us infinite gain bandwidth product, which is what is demanded by a controller of this particular structure. So how do we address this issue, and how do we achieve a controller which has a finite gain bandwidth product? This is the next question that I want to address. To address this question, let us return to the steps that we had undertaken in order to obtain the structure of this controller and determine the locations of the poles P4 and P5. So in order to determine the locations P4 and P5 of the controller, we first noted that the root locus of the overall system would have branches that cross over from the left half of the complex plane to the right half of the complex plane on account of the two poles P4 and P5, and we considered a point Q on this branch, and we demanded that the gain at which the root locus crosses over, or the gain at which the point Q will cross over from the left half of the complex plane to the right half of the complex plane, should be greater than the maximum gain that the overall open loop system would assume when we have variation in plant's parameters. So this was what was captured by the equations that we wrote 3 clips back. We determined the maximum value of gain, which is K max, in terms of the distances P1 PCL max, P2 PCL max, P3 PCL max, Z PCL max and Z bar PCL max, all these terms were known. The only term that was not known was P4 PCL max the square, and that was what had to be determined, and that had to be less than KQ, and KQ was essentially P1Q, P2Q, P3Q divided by ZQ times Z bar Q times P4Q times P5Q, and these two terms, if P4 and P5 are coincident poles, these two terms will simply be equal to P4Q the square. Now we noted that since the points P4 and P5 were assumed to be very far away from the origin, then in a plot where we indicate the locations of the 3 of the plant's poles and the 2 of the controller zeros, these 3 plant poles and 2 controller zeros that are near the origin will appear as though they just constitute a single lumped pole at the origin. In other words, the big picture of the root locus gets simplified to something that looks like this. We have one lumped pole at the origin, that is the effective contribution of the 3 plant poles and the 2 controller zeros near the origin, and then we have the far away controller poles P4 and P5, which together result in one of the branches of the root locus, namely the branch on which the point Q lies, to cross over from the left half to the right half of the complex plane. In order to determine the location of the point Q, we first applied the angle criterion of the root locus, and that is what has been done here. At the point Q, the sum of the angles subtended by all the open loop poles and zeros has to be equal to minus pi, and we have 3 open loop poles here, one effective pole near the origin which I have called as PL, and the 2 poles P4 and P5, and the 3 angles together should add up to minus pi. Since P4 and P5 are coincident poles, we get the angle subtended by the first pole near the origin, which is the angle QPL, plus 2 times the angle QP4 should be equal to minus pi. And since the point PL is situated close to the origin and we are trying to determine the point Q at which the root locus crosses over from the left half to the right half of the complex plane, we noted that the angle QPL is minus pi by 2, and that allowed us to determine that the angle subtended by each of these poles P4 and P5 at the point Q has to be equal to minus pi by 4, or equivalently 45 degrees. And with that simplified picture available to us, we could determine the distance of the point Q from the origin to be equal to the distance of the poles P4 and P5 from the origin. They both had to be equal to L, and we could then express K max as some constant times L square, because the term P4 PCL max represents the distance of the point P4 from the point PCL max which is situated very close to the origin. So for all practical purposes we could assume that the distance of the point P4 from PCL max is nearly equal to the distance of the point P4 from the origin itself, and hence we could replace the term P4 PCL max with the term L, and we would get L square in the expression for K max. And likewise in the expression for KQ, we had KQ to be equal to PLQ times P4Q times P5Q. P4 and P5 are coincident poles, so those distances are the same. From the fact that this is a right angled isosceles triangle, we noted that P4Q and P5Q are both equal to root 2L, where L is the distance of P4 from the origin, and hence, and PLQ was equal to L, and hence KQ was equal to 2L cube. So KQ was equal to 2L cube, and K max was given by this constant times L square. By setting KQ to be greater than K max, we can work out what the value of L had to be. Now these were the steps that we had adopted in order to obtain the position of the poles P4 and P5 and complete the controller design. Now suppose we want a controller with a finite gain bandwidth product. We note that we cannot have the denominator polynomial of the controller be exactly of the same degree as the numerator polynomial of the controller. This is precisely what landed us in the trouble that we just talked about a few minutes back. We ended up with a controller with infinite gain bandwidth product. So we have to have a controller that is strictly proper. or in other words the number of poles of the controller should exceed the number of zeros. So since we have to have 2 zeros in order to restrict the variation of the closed loop dynamics of the overall system, we need to have at least 3 poles for our controller. The question now becomes, how does one determine the location of these 3 poles? To address this question, we can follow the exact same steps as what we have done so far. So if we assume that we have 3 poles P4, P5 and P6, and Q represents the location at which the root locus crosses over into the from the left half of the complex plane to the right half of the complex plane, and PL represents the lumped pole at the origin, then to determine the location of Q we can once again start by applying the angle criterion. So the angle of QPL plus 3 times the angle of QP4 should be equal to minus pi. This is under the assumption that the points P4, P5 and P6 are going to be coincident, or in other words they are all going to be sitting at the same location in the complex plane. Now once again we note that the angle QPL is going to be equal to minus pi by 2, hence we would have 3 times angle QP4 to be equal to minus pi by 2, or other words angle QP4 to be equal to minus pi by 6, or equivalently it is going to be equal to 30 degrees. So unlike the previous case where we had 2 poles for the controller, if we choose to go with 3 poles for the controller, the angle subtended by these 3 poles, assuming that they are coincident, is going to be equal to 30 degrees at the point Q instead of 45 degrees as it happened in the previous case. So if I were to connect these 3 poles which are assumed to be coincident to the point Q, then the angle formed by this line with respect to the real axis is going to be equal to 30 degrees. Now what we need to determine is a distance of each of these poles from the origin. So what we need to determine is the distance L, which has been shown here. Now from this triangle we note that PLQ is going to be equal to L by root 3, because this is a triangle, a right angle triangle with one of the angles being 30 degrees, and the hypotenuse is going to be equal to 2L by root 3. So we would have K max to be equal to P1 PCL max, P2 PCL max, P3 PCL max times P4 PCL max times P5 PCL max times P6 PCL max divided by Z PCL max times Z bar PCL max. And since we have chosen P4, P5 and P6 to be coincident, we would have this to be equal to P1 PCL max times P2 PCL max times P3 PCL max times P4 PCL max the cube divided by Z PCL max times Z bar PCL max. Now we noted that the distance P4 PCL max represents a distance from the point P4 to a point that is very close to the origin, situated near the dominant poles minus 1.5 plus minus 2j. Hence for all practical purposes this distance from the point P4 to the point PCL max is approximately going to be equal to the distance of the point P4 from the origin itself. So this distance is going to be approximately equal to L. Hence we would have K max to be equal to P1 PCL max times P2 PCL max times P3 PCL max divided by Z PCL max times Z bar PCL max times L cube. That is going to be the value of K max. However, KQ is going to be equal to PLQ times P4Q the cube. I am taking P4Q the cube because we have 3 poles, namely P4, P5, P6, which are all coincident and therefore are at the same distance from the point Q. And we note that if this is a right angle triangle with the angle at the point P4 being equal to 30 degrees, then from trigonometry we see that the distance PLQ is going to be equal to L by root 3. So that is one term, and the hypotenuse of the triangle, which is going to be equal to the distance P4Q, is going to be equal to 2L by root 3, and that is going to get cubed. So we are going to have the gain at which the point Q crosses over from the left half to the right half of the complex plane to be given by 8 times L power 4 by 9. Now in order to make sure that none of the closed loop poles are going to be on the right half of the complex plane when the plant parameter changes by the maximum possible value by which it can change, we have to ensure that KQ should be greater than Kmax. The same equation has to be applied, and we note that Kmax has a term L cube times some constant whose numerical value we already know, and we note that Kq is given by 8 by 9 L power 4. So if we apply this inequality Kq greater than Kmax, we would have 8 by 9 L power 4 should be greater than P1 PCL max times P2 PCL max times P3 PCL max divided by Z PCL max times Z bar PCL max times L cube, and L cube here cancels with L power 4 there, so that we would get L should be greater than 9 by 8 times this term here, the term within the square bracket, which I shall not write again in the interest of brevity. So by applying this equation we can now obtain the new locations where the points where the controller poles P4, P5 and P6 have to be located, and if we do that and finally compute the controller gain K for this new controller, we would end up with a controller whose denominator polynomial is of 3rd degree, while the numerator polynomial would be of 2nd degree because of the 2 controller zeros that we have chosen, and hence we would have a controller with a finite gain bandwidth product. To illustrate this, I have undertaken the design for the case for the first example that we had taken up, and we see that in the blue trace is the original controller which had just a pair of poles along with the 2 zeros that were added, and this controller has infinite gain bandwidth product and is therefore not practically realizable. In contrast, through the slight modification in the design steps that we just undertook, we have ended up with a controller whose Bode plot is shown by the red trace here, and this controller has 3 poles and 2 zeros and is hence a strictly proper controller, and we see that beyond the corner frequency of 39 radian per second, the magnitude characteristic falls down at minus 20 dB per decade, and hence this controller will have a finite gain bandwidth product and hence would also be practically realizable. The third and final aspect of root locus based 2 degree of freedom control design that I wish to discuss is concerning the number of lumped poles that we have near the origin. If we return to the original root locus of the overall system, we notice that we could exploit the fact that the 3 of the plant poles and the 2 controller zeros were very close to the origin compared to the 2 controller poles P4 and P5. In order to lump the effect of these 3 poles and 2 zeros as just a single lumped pole at the origin. If the plant had 4 poles instead of 3 poles and we had added our 2 controller zeros, then the effective number of poles or the lumped poles near the origin would have been 2, namely the difference between the number of poles and the number of zeros, because very far away from the origin this collection of n poles and m zeros will simply look like n minus m poles sitting at the same location. Hence, can we allow the number of poles near the origin to be anything other than 1? Can it be 2, can it be 3, or can it be 0? This is the question that we shall try to answer in this last segment. So, in the first example we considered that we had one pole near the origin, and because we had one pole near the origin, if we considered the point Q on the branch that was about to cross over from the left half to the right half of the complex plane, we could conclude that this one lumped pole subtended an angle of minus 90 degrees at the point Q. The negative sign comes because this is a pole that is subtending the angle and not the 0, and hence the other poles P4 and P5 needed to together subtend an angle of 90 degrees at the point Q, and if the points P4 and P5 were assumed to be coincident, then each of them ended up subtending an angle of 45 degrees at the point Q. But suppose instead of having a single lumped pole near the origin, we had two lumped poles near the origin. I shall redraw the complex plane in order to depict this scenario. So, we have two poles near the origin, and we also have our poles P4 and P5. What is going to be the consequence of having two lumped poles near the origin? We would have these two lumped poles if our plant was a fourth order plant and we had just two controller zeros. Then we note that in the vicinity of these two lumped poles, each of these poles subtend an angle of minus 90 degrees, and hence the two together subtend an angle of close to minus 180 degrees. What this indicates is that the root locus will cross the imaginary axis at a point that is situated very close to these two lumped poles. In other words, I will have no control over the location at which the root locus crosses over from the left half to the right half of the complex plane by appropriately positioning the faraway controller poles P4 and P5. This is in contrast with the first case, where by appropriately locating P4 and P5 at a sufficiently far away distance from the origin, we could get our closed loop system to be stable even when the plant's gain assumed its maximum value possible. However, in the case where we have two lumped poles near the origin, since the root locus crosses the imaginary axis at a point that is very close to these two lumped poles, because each of these poles contribute to approximately minus 90 degrees phase, and therefore together they contribute to close to minus 180 degree phase, these faraway controller poles have very little role in determining the location at which the root locus crosses over. Hence, there is no way in which we can guarantee that our closed loop system is going to be stable by appropriately positioning the points P4 and P5. So, what is the remedy if we are stuck with such a situation? The remedy is to add one more controller 0 near the origin, so that the net number of poles and zeros near the origin would be 1 instead of 2. This problem also exists if we have the number of poles, lumped poles near the origin to be more than 2. So, if it is 3 or 4 or any other number apart from 1, then we would have no control over the location at which the branches of the root locus cross over from the left half to the right half of the complex plane by suitably changing or controlling the positions of the points P4 and P5, the far away poles of the controller. Hence, if we are lucky, then for the maximum variation in the plant's parameters, our control system would be stable, but there is no way whereby we can design the control system to be stable by suitably choosing the structure of the controller. Hence, we need to make sure that the number of lumped poles near the origin is 1 or less. Now, if we look at the next situation, which is the opposite of what we have been looking at now, namely where we have no poles at all near the origin, or in other words, we have the complex plane, and in the complex plane there are no lumped poles near the origin, and we just have the two controller poles P4 and P5. What will the consequence be? We note that If we have no lumped poles near the origin, then it means that all the branches of the root locus near the origin that have originated from the poles near the origin have already sunk into the corresponding zeros near the origin, and there are no branches coming out. So the only branches will be the branches coming from the points P4 and P5, and if P4 and P5 are separated from one another, then we would have a branch originating from each of them. They collide at their midpoint and then break away into the complex plane. The angle at which the asymptotes of these two branches of root locus tend to infinity will be plus minus 90 degrees. So what we would see in this case is that we would have no concern about the instability of the overall closed loop system because of these branches of root locus. That is because these branches of root locus will always subtend an angle of plus 90 degrees or minus 90 degrees with respect to the real axis, and hence will never cross over from the left half to the right half of the complex plane. So since no issue of instability arises in this scenario, there is no need for us to undertake the elaborate design steps that we undertook in the first case, where we had a single lumped pole near the origin, in order to determine the location of the points P4 and P5 to ensure that the closed loop system is stable even for the maximum permissible variation in plant parameters. Hence the last note in association with 2 degree of freedom control design performed using the root locus is that we have to ensure that the number of lumped poles near the origin, or in other words the difference between the number of poles and the number of zeros placed near the origin, should be equal to either 1 or 0 in order for our closed loop system to be stable. If we are given a plant whose degree is such that the number of lumped poles is more than 1, then we have to add enough controller zeros near the origin to ensure that the net number of lumped poles near the origin remains either equal to 1 or 0. With this we conclude our discussion on 2 degree of freedom control design to achieve robustness against plant parameters performed using the tool of root locus. Thank you.